starting off with the first example on page 40, let's go ahead and draw a ray diagram, and then we'll go to the board and confirm with our math. So start with a principal axis and a principal plane. Draw on your lens and be careful to measure out the distances for the focal lengths. Okay, again, not important what you make them, but important that you make them the same length on both sides. Don't forget, it's switched from yesterday's converging lens, right? Because parallel rays will diverge and then appear to focus here. And that is where we decide the principal versus the secondary, is where would parallel rays from the object converge or appear to converge. So now the principal focus is on this side. Okay, so a 3 centimeter high object, that's HO, located at 15 centimeters, DO, from a diverging lens with a focal length of 10 centimeters. Remember, that focal length is going to be negative because it's a virtual focus, right? Parallel rays are only appearing to focus there, whereas yesterday on our converging lens, any parallel ray really was passing through the focus, so it was positive. Real upright, 6 centimeters high, HI, located 60 centimeters from the lens. Let's see if we get that from the ray diagram. There, it's at 15 centimeters and the focal length is 10, so it's actually at exactly 1.5 focal lengths. So we can throw that in if we want to be super careful. What's important though is just that you put it between the focal length and twice the focal length. Other than that, doesn't really matter. But let's go ahead and be perfectionist with it. Why not? There's my object. Rule 1, parallel to the principal axis, hits the principal plane, and by the way, guys, remember, use your knowledge of the lens. So I get it. Your instinct, honestly, even mine, you probably saw, I almost did it there, right? Is to go through this focal length. But ask yourself, is that what a diverging lens would do, right? Even if you can't remember that a diverging lens should always make it spread out, fall back on your knowledge of refraction, right? If the normal's here, right, it should bend towards the normal because it's getting slowed down. And then on the other side, it should get bent away from the normal because it's getting sped up. So fall back on your knowledge if you're ever unsure on a ray diagram what the rules are, right? You can always fall back on your knowledge and get an idea. So that gets projected back through. Okay, let's go ahead and do rule 2, the easy one. Through the center, no refraction, or at least no net refraction, because whatever happens on the way in gets undone on the way out. Okay, again, yeah, real ray does come from there, okay, but if we wanted, we could project it back and still get the same result. Finally, one headed toward the secondary focus will get refracted parallel, but when our eye projects that back, it will see this. Okay, and we're feeling great about that because all three intersected at pretty much the same spot. We're also feeling good about it because we know what a diverging lens should produce. It should make a virtual, erect, and diminished image. And I'm just realizing, should have read the question more carefully. This is what a student found. We're trying to figure out if they're right, okay? Because it says evaluate the student's findings. So let's hop over to the math to do that. However, we can already say this student is wrong, right? In fact, even without drawing the ray diagram, we probably could say the student was wrong because we know that a diverging lens should produce a virtual image. So real? No way, right? Impossible. Even without the ray diagram, we knew that, but definitely not with the ray diagram. Upright, okay, that's okay for a diverging lens, and that's what we got for our ray diagram. 6 centimeters high, well, let's look, the object was 3 centimeters high, so this would be enlarged. Diverging lenses can't do that, and our ray diagram can back us up there, so yeah, no, right? Located 60 centimeters from the lens, well, again, our ray diagram tells us it should be closer. We also might just know that from a diverging lens, right? These correct nearsightedness by making the object appear nearer, so wrong. Plus our ray diagram says that. Okay, let's go see if what our math says. Okay, so let's go ahead and see how the math backs us up on this one. So a 3 centimeter high object, again, that's HO, height of the object, is located at 15 centimeters from the lens. So that's the distance of the object with a focal length of 10 centimeters. Now this is a diverging lens. So what does that mean about the focal length? It means it's negative, right? So negative 10 is the focal length. A student now analyzes the situation and determines if the image is real, upright. Like we said, if we know our stuff about a diverging lens, we should already know that's wrong, right? It can't be real. It should be virtual. Upright, yeah, that's okay. 6 centimeters high, that's bigger, so that's not right. It should be diminished, okay? And 60 centimeters from the lens, again, that should be closer. Let's see what the math says, though. So we have 1 over f equals 1 over do plus 1 over di. To compare to their findings, we need to find di. So subtract 1 over do from both sides, and then we just flip both sides, do both sides to the power of -1, or 1 over both sides, then we will have di equals 1 over f minus 1 over do, all to the power of -1. Okay, and we can plug in. Be very careful, 1 over -10 centimeters, because that is a virtual focal point. That's not a real focal point. Okay, let's do this one without a calculator just for fun. Okay, so we have 10 and 15 in our denominator. Let's do 30 as our common denominator. So 1 over 10, if I multiply by 3 over 3, that's the same as 3 over -30. Okay, minus 1 over 15, if I multiply by 2 over 2, I don't change the number, but I do change the denominator so that I can do that subtraction. Okay, so it's 3 over -30, yes, but same thing as -3 over 30, right? That's the same number. 3 over -30 is the same number as -3 over 30. Doesn't matter where you put the negative. So then I have -3 minus 2. -3 minus 2 is -5 over 30 cm to the -1, which is the same as 30 cm over -5, which 30 over 5, that's 6. So -6 cm is the distance of the image. So what does the negative tell us? It tells us it's virtual. Okay, and it tells us it's 6 centimeters from the lens, which allows us to say this is wrong and this is wrong. All right, to evaluate their height findings, which again we know are wrong because we know how a diverging lens works, but let's just try it out. We have that HI over HO equals -di over DO. If we wanted to find the magnification, we could. The question didn't really ask us for it though, so we can kind of skip that step. So di is -6 centimeters. Don't drop that negative. Height of the object was 3 centimeters divided by the object distance, which was 15 centimeters. And I got to 2 sig digs that the height of the image was positive 1.2 centimeters, right? Negative times negative is a positive. So what does that tell us? It tells us it's erect, and 1.2 is smaller than 3, so it's diminished, okay? If you wanted, you could also just work out the magnification, and you would get positive 0.4x. So that means smaller because it's 0.4, right? It's going to be 0.4 times as big, and it's positive 0.4, so it'll be erect. Okay, so just like our diagram said, we got that it was virtual, diminished, and erect from the math, and that tells us that this is correct. However, this is wrong. Okay, let's do the next one a little bit different. First, I'll do the math, and then we'll check with the ray diagram. So I know the ray diagram's already there, but I'll do it on paper with you after this live. Okay, so this is a fun one to do with the math because we have to think. So describe the characteristics when the object is very close to the diverging lens. So how I'm going to interpret that is, let's let DO approach 0. Okay, we'll let DO go close to 0. Okay, or we could just say let DO be way less than F. Okay, it's much smaller than the focal length. So then when we say 1 over F equals 1 over DO plus 1 over DI, and we have 1 over F minus 1 over DO equals 1 over DI. And then let's stop and think here. So if DO is much, much smaller than F, how do these two numbers compare? If DO is very, very small, then 1 over DO is very, very big. And 1 over F is very, very small compared to this number anyway. So if DO much less than focal length, then 1 over DO is actually much greater than 1 over the focal length. So we could say that 1 over the focal length minus 1 over the object distance, well, that's essentially, if this is barely going to make a difference, we could essentially say it's 0 minus 1 over DO, right? So essentially, this would be equal to -1 over DO, or approximately equal. At least we can estimate it to be about that. Okay, well then, what do we have? Then the -1 over DO, which is just the left side of the equation up here, right, is essentially equal to 1 over DI, is approximately equal to 1 over DO. So then, therefore, flipping both sides, we have -DO, okay, could be approximated as DI. Now, pause here for a sec because Are we saying that the image distance is going to essentially be there? No, right? They're not actually equal. Remember, 1 over f is, we're going to say it's nearly 0, but it's not actually 0, right? This is a number that's going to make what negative 1 over do is still a little bit shifted because of that 1 over f. So we could say the absolute value of 1 over do, though, is still smaller than the absolute value of 1 over di, right? Because this had that 1 over f, as tiny as it was, it still had that 1 over f. It still had that 1 over f, which would be negative, because focal length would be negative. So we had a negative minus, so we had a very small negative number minus we had a very small negative number here minus a big positive number. So 1 over do will be slightly smaller than 1 over di, okay, absolute value-wise, which means that do, that's because that is slightly, because of that 1 over f that we sort of ignored, right? But can't completely ignore, slightly bigger than 1 over di, or slightly bigger than just di, sorry. So you can see as the do basically becomes 0, right? Di gets closer and closer and closer to the di gets closer and closer to being di. It can never be the exact same, but di kind of approaches do as do approaches 0. So what does this tell us? Well, if negative do is di and do is kind of by default positive, then this tells us that di will be negative, so image will be virtual, located very close to object, but still closer to lens than object. Okay, what about for the magnification or for the height? Well, let's do magnification this time. So if m equals negative di over do, and we're saying negative di over do are pretty close to the same. Of course, they're not the exact same, but, and so that is negative do over do, right? Which is about equal to 1. So again, realistically, it would be slightly less than 1, but it is positive. That part's right. It's erect, okay? And it's approaching erect, and it's getting very close to being the same size as do, but it never will be the same size as do, right? Do, the place at which it becomes the same size is when do is 0, and do can't be 0. Okay, so erect, hi is close to ho, but still slightly smaller. Okay, this is one that definitely would make more sense to go at with a ray diagram, right? That's some kind of weird math to wrap your head around. Just bang out a ray diagram, okay? Or just remember that it's a diverging lens, right? It will always, always, always be virtual, erect, and diminished. Just the amount that it's diminished is what changes with object distance. Okay, and again, test tip, if you're writing a multiple choice test and you're trying to save time, right? Helps to just remember that a diverging lens always produces closer images that are upright, smaller, and virtual, right? Then you circle the right answer and move on. Still, we should have this skill down, so let's go ahead and practice it. Just a test tip there, right? Don't need to draw a ray diagram if you know all that stuff and you're pretty confident on it. But being able to fall back on drawing the ray diagram, right, important as well. Okay, principal axis, principal plane, lens, measure out the focal length, and twice the focal length, and the secondary focus, and twice the secondary focus. So when the object is very close, so let's just put it right next to the lens. There's our object. Okay, but nothing changes. Still parallel to the principal axis. Okay, then remembering that the rays get spread out, we'll go up this way and say to ourselves, okay, diverge, but projected back through the primary focus. Okay, anything headed towards the secondary focus gets refracted parallel, which means our eyes would project it back. Okay, you can see the intersection is happening very close to the object here, right? And if we go ahead and do our center one, notice they're intersecting like right there. So it's still virtual, it's still diminished, still erect, still closer to the lens than the object, but that difference is now less exaggerated, right? As we approach the lens, the image is approaching the object size, approaching the object distance, but staying virtual, of course, okay? Which we saw in the math. As the DO approaches 0, right? Well, then DI approaches DO, HI approaches HO. Never quite gets there because the object can't be at 0, right? But as it approaches, that's what happens. So like our math said, closer, upright, smaller, virtual. Or just like our noggin said, right? Because we knew that for a diverging lens. Okay, and let's do these kind of wrap up type questions that just kind of bring it all together now. Okay, so this is a question from an old diploma. It says students use 3 of the apparatus illustrated below to produce a focused, real image in a darkened room. One of the apparatus has a focal length of 10 centimeters. Now they place these apparatus at each labeled location, so at X, at Y, and at Z on an optics bench below. The optics bench is scaled in millimeters and labeled in centimeters. So important to know that this is 0 centimeters, 10 centimeters, 20, 30, etc. So let's eliminate what we can here. So if we're going to place it, before we even think about our placements, look at this. The image is real. Okay, it's real. What can produce a real image? Well, if we're talking lenses, we know a diverging can never produce a real image, right? So maybe a converging lens, we'll see. If we're talking mirrors, we know a plane mirror can never produce a real image. We also know a convex mirror can never produce a real image, right? They always produce virtual, diminished, and erect. Here's something that we should know going forward, okay? See these kind of little ticks there? You might be thinking, well, how do I know if it's a convex or a concave mirror? It depends which side I send light in from. Those little kind of ticks on the side there, that means that's not a reflective surface. That's like the inside of the mirror, okay? So that means that this side is the reflective side. So this is a concave mirror, okay? A converging mirror. This one would be a convex mirror. Convex mirrors cannot produce real images, right? They can only produce virtual, erect, diminished. So that is also eliminated. Okay, now I know we haven't talked about it till the next section, but if you came back to this one later, you would realize diffraction grating to produce an image, that doesn't even make sense, right? They don't really produce images. They don't focus stuff. Okay, same goes for a double slit apparatus. A double slit apparatus is just a more simple diffraction grating, really. Now a screen, how are you going to produce an image without a screen? Okay, screen, no matter what our answer is, our answer, I can tell you right now, is going to have 9 in it. Okay, no matter what, our answer is going to have 9 in it because you can't make an image without something to project it on, right? Like I did on the whiteboard with the lighter in the lens. Okay, so there must be a screen. When it comes to our light sources here, this is a little bit, I think, just a trick to throw you off. Okay, looking at 0 and 1, it doesn't matter what your light source is. You're going to need a light source to produce an image. You can do that with a laser. You can do it with a candle. If it were me writing this, I would probably use 1 just to be extra safe because that's usually what you use. But you can make an image with pretty much any light source, okay? So our answer could have 0 or 1 in it as the light source. We're going to need something because it's a darkened room, right? But which one doesn't actually super matter. Let's first, just as the lower number, let's look at the lens. Can we use the lens to produce a real image? We know converging lenses can produce a real image, but with this setup, could we do it? So how are we going to do that? Well, let's just think, okay? If we put let's say we put the candle here, okay? We put the candle at location X, well, then we would have to put the lens at location Y and the screen at location Z, okay? So let's see what happens there. So let's just write this in to think about it. So if we did 1 candle there so that the light could leave, go through the lens, and maybe get focused at 9, will that work? Okay, we have to check. Would a real image be produced there? So checking for 1, 2, 9 as an okay answer. Let's see. How are we going to figure this out? Well, 1 over F equals 1 over DO plus 1 over DI. Okay, now this is important from the question. One of the apparatus has a focal length of 10 centimeters. Don't make the mistake of thinking, oh yeah, converging lens can produce an image. Must be that works, right? Be careful. If they give you a number, check with the math. So if one of the apparatus has a focal length of 10 centimeters, the candle doesn't have a focal length, right? The screen doesn't have a focal length. That means our converging lens has a focal length of 10 centimeters. So it's a converging lens, so that's a positive focal length. 1 over 10 centimeters equals 1 over. So what is DO then? Well, we have here that location X is at 5 centimeters. Location Y is at 20 centimeters. So DO in this case would be 15 centimeters. Okay. Now, if this works out, DI should be about 15 centimeters. We want the image to form on the screen, right? So we need 15 centimeters to be where the image forms, or close to it anyway. Okay. So 1 over 15 centimeters plus 1 over DI. Whoops, I should have manipulated first. Oh, well, we'll do an L. 1 over 10 minus 1 over 15 equals 1 over DI. Okay, flip both sides. Okay, and I got that DI equals 30 centimeters. Okay, now let's think about that. Where's the image forming? Well, it's forming way over here, right? Way over here. Way behind the screen, way over here. That's no good to us. That's like being a very far-sighted person, right? That's no good. No clear image would be produced, right? And it even goes to the trouble of saying focused. So that's no good. We would need the image to form somewhere else for that to work. Okay, so it can't be the lens, right? So it can't be the lens. So our answer will not have 2 in it. So no good. 129 is not an appropriate answer. Let's just double check that mirror if we want to be really careful. You could probably guess how it goes together if you were actually writing this test and trying to save time, but let's go through and see why it's definitely the right answer. Okay, so let's use the candle again. Why not? Okay, so if we put the candle here, let's say, are we still going to put the screen here if we have a mirror? No, right? Because where's the image going to form? The light's going to have to leave the candle, bounce back, and then hit a screen, right? If I put the mirror here and the screen over here, what's going to happen? Light leaves, bounces away, never gets to the screen. So we need to put the screen here if we're using a mirror, and then put the mirror down there. Is that an okay option? Do it in black. Well, if I'm putting the light source here, 1, okay, and I'm putting the screen here, and I'm putting the object mirror here, then distance object is between the light source and the mirror, right? That's the distance object. So that would be from there to there. So 15 and then another 15. So this is 30 cm. That would be our DO now, right? So we have starting here. Okay. Now the thing with a focal length of 10 centimeters is going to be our mirror, right? Same idea, just because the question told us it was going to have something has a focal length of 10 centimeters. It's not the screen, it's not the candle, so it must be the mirror. So just going to jump to here because it's the same manipulation. Okay, DI equals 1 over positive 10, positive for a converging mirror because it really is focusing light rays there. It's a real focal point. Minus 1 over DO is now 30 cm to the minus 1. If you plug that in, you'll get that the image distance is going to be, a perfect 15 centimeters, meaning that the image will be formed right here, right? Positive 15, so it's real, which for a mirror, if a mirror is placed there, right, that is where the screen will be. And exactly where it should be, we have a real image forming, real because it's positive, right? Everything checks out perfect about this answer. So 194, that works perfectly. This diploma would actually have taken more than one answer for this, right? Because you could have used the laser. There's nothing wrong with using the laser. So 194 would absolutely be correct. However, putting a laser in instead of the candle, that would also work. So you could have done 094 as well. And again, you could actually do 2 more answers because what's wrong with putting the mirror here and the candle here instead, right? So you could have done 491 and 490. Just flipped them around. Okay. Yeah, I know the mirror looks like it's stuck one way, but you're allowed to flip it. It's just where you're going to put it. Now for this one, okay, a group of students measures an object to be 10 centimeters tall. So that's the height of our object, HO. The height of our object, HO. Okay. They place the object 3.2 centimeters in front of a thin lens. So that's DO. They observed that a virtual image, okay, virtual image, so whatever DI is, it's going to be negative, is formed and measure the distance from the image to the lens to be 4.3 centimeters. So that's DI, but negative DI, right? DI should be negative 4.3 because it's virtual. Okay, a couple things. You can, if for test smartness, if you're looking to eliminate 2 answers, we can actually eliminate 2 right away here. Know how? Well, take a look at our DI, take a look at our DO. And then think about the fact that this is a virtual image. So it being a virtual image doesn't eliminate any type of lens. However, the fact that it's a virtual image and that it's appearing farther away than our object, right? That does, those two facts together eliminates a diverging lens. Because yes, a diverging lens produces virtual images, but it produces virtual images that always appear closer to the lens than the object. So this is not a diverging lens. Now, if you're panicked right now thinking, oh God, I have to memorize that, I mean, it doesn't hurt to memorize it, okay? But you're okay here. We can still get it from our equations as long as you remember your signs, okay? So 1 over the focal length equals DO plus 1 over DI. Now, if I find the focal length and it's negative, that's a diverging lens, right? Because they don't actually make light converge. They appear to do it. It's a virtual focal point. But if I find the focal length and it's positive, then that's a converging lens because it's a real focal point. They really do that. So let's find the focal point. I'm just going to flip both sides. F equals, okay, I'm going to have to find the focal length anyway to answer the second part of the question. So 1 over DO. Okay, 1 over DO is 3.2 centimeters plus, now don't forget the negative here, 1 over negative 4.3 centimeters, right? So we're actually going to subtract this from that. So then the focal length ends up being 13 centimeters, okay? Now it's positive, so probably the safer way to answer the question than relying on your memory too hard, right? Positive focal length gives us a converging lens, right? Because it has a real focal point. It actually focuses real rays. It doesn't just appear to focus virtual rays. So converging and 13 centimeters. That 1.8, that's the answer you get if you drop the negative. Sneaky, sneaky. Be careful. Last one here for this topic. When we look at, so we have here two images of the sun, one taken in the visible light spectrum and one taken in the X-ray spectrum. So you can see definitely it's brighter in the visible light spectrum. Still some bright spots in the X-ray spectrum, but less so, right? Now, this is a very common practice in astronomy. Take a picture with different filters on your telescope, okay? So we can look at EMR coming to us in the visible light. We can look at EMR coming to us in the X-ray by putting on the right filter. You'll notice the sun is actually not a super hot star, right? That's why it's emitting way more in the visible light than in the X-ray. Remember, what produces EMR? An accelerating charge. How do you make a charge move? Well, you need energy, right? Thermal energy could do that because thermal energy is just the motion of particles anyway, once you get down to it, right? So its charged particles are not vibrating fast enough to produce a lot of X-rays. Clearly some are, right? But remember, EMR has the same frequency as the accelerating charge which produced it. So to get high frequency, low wavelength X-rays, you need to be vibrating pretty quick. Hotter stars, when we look out at hotter stars in the universe, we can see quite a bit more X-rays being produced, especially when we start to look at weirder things, even higher energy than just plain old stars. Okay. All right. Anyway, back to this. So it's asking us, after viewing the object using visible light, we need to make adjustments if we're going to view the same object using X-rays. So if we have a telescope and we want to switch from the left side to the right side, we can't just put on our filter. We're gonna have to play with the telescope a bit. Okay. So just gonna go down here to this kind of focusing question here. Compare visible light to X-rays. An adjustment must be made because, so why must an adjustment be made? Well, think about that. What's different about X-rays and visible light? Well, X-rays, like we just said, X-rays have a much shorter wavelength, right? Okay. Now, what do we know about shorter wavelengths when it comes to refraction? Think about blue light and red light, right? Which one gets refracted more? Blue light. So in this case, X-rays are like the blue light, visible light is like the red light. So X-rays, so they will refract more. Okay, they will bend more. They will focus earlier. Again, just by the fact that N2 over N1 equals lambda 1 over lambda 2. If you just rearrange this a bit, you get lambda 2 N2 equals lambda 1 N1. Okay, if you have a smaller wavelength, like an X-ray, versus a bigger wavelength, like a visible light, how do you keep this equation equal? Well, smaller wavelength, higher index of refraction, higher wavelength, smaller index of refraction to keep both sides equal, okay? Higher index of refraction, again, means bend more, okay? So how do we fix this? Or first, let's visualize it. What are X-rays gonna do? They're gonna focus too early. So they're gonna come in parallel from the sun, and then they're going to bend more, right? parallel from the sun, bend more than visible light would. That one's still going to go through the middle, bend more, bend more. So it's going to focus too early, right? So let's think about this. What can we do? We need to make the changes that will cause it to focus later. So that's option one, make it focus later. Okay, that's one way we could fix this. Okay, let's just say, here's our two main overarching things. We need to make it focus later. Or, or what if we just said, okay, it's focusing early. What if we could just decrease the distance from the detector to the lens, right? That's another way we could fix this. So we could move the detector, right? If the detector's here now and it's too late, right? Well, why don't we just move it closer so that it focuses at the right place? Essentially, this is a nearsighted telescope now once we switch to X-rays, right? It's the light is focusing too early. So if you could squeeze the back of your eyeball forward, that would fix your nearsightedness as well, although I don't recommend it. It's a lot easier just to get glasses. Okay, make light focus later or decrease distance from lens to detector. So any option that kind of gives us those two things, those will work. Go three. Hey, move the lens closer to the detector. Well, that would work, right? If I move the lens backwards, there we go. You can kind of think this whole thing would just, this whole stuff would just shift until the focal point was in the right place. So absolutely, that'll work. Move the lens further from the detector. Well, is that going to help us? No, that'll make the problem worse, right? That's no good. Okay. Move the detector closer to the lens. Yeah, right. It doesn't matter which one you move as long as you make them closer together. Okay. Move the detector further from the lens. Again, no, that's no good. That'll make things worse. Okay. Use a lens with a lower refractive index. Lower refractive index. Does that mean bend light more or bend light less? Right, that means bend light less, lower refractive index. So what'll that do? It'll make light not focus so early. Maybe it'll focus in the right place, right? It'll focus back here more. So yeah, that's good. We could do that. Okay, that'll help us out. But use a lens with a higher refractive index. That's going to make light bend even more and focus even sooner. So that's no good. Move the object closer to the lens. Okay, let's think about this. What is the object here? It's the sun, right? How much closer are you going to get this telescope to the sun realistically that's going to actually make a difference in where the object is, right? The sun is so incredibly far away that pretty much no matter what, you're going to get parallel rays coming in, right? Unless you actually send this thing out into space, that's really not going to make a difference on where the image is focusing, okay? The rays are the rays are essentially going to come in parallel. If we were dealing with something much closer, then yeah, the rays might not be coming in parallel, and we could maybe talk about that. But this, it's ridiculous, right? To even think about that. Realistically, once you get past even a few focal lengths, you're talking about rays that are basically coming in parallel, right? If you're nearsighted, you know that. Doesn't take long before rays are coming in parallel and you can't see very well. At least if you're like me, I don't know. Okay, so move object closer to lens. No. Move object further from lens. No, we're talking about the sun, right? There's nothing we can realistically do with the sun to actually make it. So context matters for these questions, right? Do think about what the object is. It's the sun. Okay, you can't really do that here. Use a lens with a larger diameter. Diameter, when we're talking about lenses, refers to this axis. Okay, so the axis of the principal plane, essentially. If we make this thicker, sorry, not thicker, if we make it taller, if we make it wider in terms of diameter, right? Does that change where the light is focusing, right? If I'm a parallel ray and I come in and everything else is the same, no, right? It's still a parallel ray hitting something with the same refractive index. So what a larger lens can do in terms of diameter, what it can do is, and you'll see this if you do the virtual lab for this week, okay? But it collects more light. It gathers more of these parallel rays. So what it can do is produce a better image, a brighter image. But what it does not do is change anything about the image other than that, other than the quality of the image, basically. Okay, so diameter has no effect on any of that. So which of these adjustments would actually help us here? Looks like 1, 3, and 5. Okay, that really wraps up topic 2. So you can now check the Google Classroom or the agenda for the practice questions that go with that stuff.